Welcome back to the Explainer. Today, we're putting on our detective hats. We're going to crack the code of the atom, following the clues, the dead ends, and the flashes of brilliance that led scientists to finally understand what's going on inside.
So picture this. For literally centuries, everyone thought the atom was it, the smallest thing possible, indivisible, the end of the road. But you know what? A tiny spark of static electricity, yeah, the kind that makes your hair stand up, was about to blow that whole idea wide open and change everything. All right, so here's our game plan for this investigation. First up, we'll see how that whole unbreakable atom idea got completely shattered. Then we'll check out the very first, kind of weird sketch of what might be inside. After that, this is the good part, a revolutionary experiment that just changes everything. That leads us to a way better model, and finally, we'll decode the atom's own personal ID card, what makes each element totally unique. Okay, so let's start at the beginning. We're about to see a belief that stood for thousands of years just crumble. You gotta understand, for most of the 1800s, John Dalton's theory was king. It said atoms were these tiny, solid, indestructible balls. That was it. You couldn't get any smaller. End of story. But then there was this nagging little problem: static electricity. I mean, think about it. You run a comb through your hair on a dry day, and suddenly you can pick up little bits of paper. How? Why? Scientists started to realize that when you rub things together, you're creating a charge. And that was the first huge clue. It basically screamed that atoms couldn't just be these neutral, solid things. No way. They had to have smaller, charged bits and pieces rattling around inside. So, that discovery led to the very first real attempt to draw a map of the inside of an atom. And honestly, it's a pretty wonderfully weird picture, cooked up by the physicist J.J. Thomson. So this is the guy, J.J. Thomson, and in 1897, he makes a huge discovery. He finds the electron, this tiny little particle with a negative charge. This was massive. We're talking Nobel Prize-winning stuff. And it totally forced everyone to rethink what an atom actually looked like. So, what was his big idea? They called it the Plum pudding model. Just imagine a ball of, positively charged pudding, and stuck inside, like raisins or plums, were these little negative electrons. You could also think of it like a watermelon. The positive charge is all the pink stuff, and the electrons are the seeds scattered around. It was a pretty neat idea, actually, because it explained why atoms are normally neutral. All that positive pudding was perfectly balanced out by the negative electrons. Made sense, right? Okay, so the plum pudding model was clever, for sure. It explained why stuff wasn't constantly zapping us with electricity. But it also made a very specific prediction. If an atom is really just this soft, squishy ball of charge, what would happen if you shot something tiny through it? Well, it should just zip right through, maybe getting nudged a tiny bit, but that's it. It's like firing a BB gun into a fog bank. And, that idea was about to be put to the ultimate test. All right, now we get to the real turning point in this whole detective story. This is where one incredible experiment comes along and just completely blows the plum pudding model out of the water. So a guy named Ernest Rutherford, who, fun fact, used to be one of Thomson's students, comes up with this brilliant experiment. The plan seemed simple enough. Take a beam of tiny, fast, positively charged things called alpha particles and fire them at a piece of gold foil. And I mean incredibly thin gold foil, like only 1,000 atoms thick. The expectation? Based on the plum pudding model, those particles should just sail right through like it's nothing. But what they saw was absolutely not what they expected. I mean, it was shocking. Sure, most of the alpha particles did go straight through, just as predicted, and a few got knocked off course a little bit. But, and this is the part that changed everything, every once in a while, about 1 in 12,000 times, a particle would hit that foil and bounce almost straight back at them. Rutherford's reaction was priceless. He said it was like firing a 15-inch cannonball at a piece of tissue paper and having it come back and hit you. It just didn't make any sense with the old model. There had to be something small, dense, and powerful inside that atom. This one result just completely rewrote the book on the atom. The whole soft pudding idea? Gone. Rutherford figured out that all the positive charge and almost all the mass must be crammed into an unbelievably tiny, dense center, what he called the nucleus. And what did that mean for the rest of the atom? It's mostly empty space. That's why most of the particles flew right through. The ones that bounced back, those were the unlucky few that made a direct hit on that tiny, solid nucleus. So Rutherford's nuclear model was a huge leap forward, but it created a brand new, massive problem. See, basic physics at the time said opposites attract, right? So why didn't the negative electrons, which are orbiting this new positive nucleus, just lose energy and spiral inwards, causing the whole atom to collapse in on itself? I mean, they should have. If the theory was right, matter, as we know it, shouldn't be stable at all. So what was going on? This is where our next detective, Niels Bohr, enters the scene. And he came up with a solution to this stability problem that was, well, it was elegant and frankly, pretty strange. Bohr's idea was totally out there for the time. He basically said, what if the electrons can't just orbit wherever they feel like it? He proposed that they're locked into very specific orbits, or shells, kind of like planets in a solar system, but with strict rules. Each shell has a fixed energy level. And here's the kicker. As long as an electron stays in its designated shell, it just doesn't radiate energy. It can't spiral in, it's stable. It was a bizarre idea that broke some old rules of physics, but it worked. It explained why atoms don't just collapse. Okay, so now we've got the basic picture. A tiny nucleus at the center with electrons zipping around in their special, stable orbits. With this framework, scientists could finally start to figure out the big question. What actually makes an atom of gold different from an atom of oxygen? The last major piece of this puzzle clicked into place in 1932. A scientist named James Chadwick found a new particle hiding out in the nucleus. It had mass, almost the same as a proton, but it had no charge at all. It was neutral. He called it the neutron. And this finally explained where all the extra mass in atoms was coming from. So, with protons, neutrons, and electrons all accounted for, we could finally define what gives an element its identity. And it all boils down to one thing, the number of protons. We call this the atomic number, or Z, and it's like a unique fingerprint for every element. If you have 1 proton, you are hydrogen, period. If you have 6, you are carbon. It doesn't matter how many neutrons or electrons you have, that proton count is the element's unchangeable ID. And on top of that, we have the mass number, which we call A. This one's super simple. It's just the total number of protons and neutrons added together in the nucleus. Since electrons weigh next to nothing, this number basically tells you the total mass of the atom. And what's really cool is how chemists came up with a simple shorthand to show all of this at once. You write the mass number on top, the atomic number on the bottom, right next to the element's symbol. So if we look at this nitrogen atom, you can see right away it has a mass of 14 and an atomic number of 7. That means 7 protons, and if you do the math, 14 minus 7, it's got to have 7 neutrons too. All that info right there. And that brings us to a really neat idea called isotopes. Take a look at hydrogen here. All 3 of these are hydrogen because they all have exactly 1 proton. But look at the neutrons. The first one has 0, the next has 1, and the last one has 2. That means they all have different mass numbers. They're all the same element, they just have different weights. Those are isotopes. So there you have it. We've gone from a solid, unbreakable ball to this amazing little solar system. We've cracked the atom's code. But you know, this incredible picture with all its weird rules about electrons being locked in specific orbits, well, that wasn't the end of the story, not by a long shot. In fact, it was the beginning of something even crazier and more profound, the mind-bending world of quantum mechanics.